a few more examples of being able to identify the key components of these rational functions we're going to look at. And so we have this rational function, 18 minus 2x squared plus 18x plus 15. First thing we're going to do, find the domain. To find the domain, we set the denominator to not equal 0. We can factor this. We need two factors of 15 that are going to add up to 8. And 3 and 5 are pretty easy ones to see work. And so that would mean, and that's a not equals, by the way, not plus minus. And that would mean that x cannot be equal to -3 or -5. Okay, and we could see that because x plus 3 would not be equal to 0, and x plus 5 would not be equal to 0. So x could not be equal to -3, and x could not be equal to -5. Right? And so our domain, x would be an element of -infinity to -5, union -5 to -3. So just going in order of these places where it can't be equal to 0, and then -3 to infinity. All right, so that's not too bad. That's stuff that we've been doing all semester. Next thing we're going to do is we're going to identify the equation of the horizontal asymptote if one exists. And so what we're going to do is we're going to compare the degree of the numerator and the degree of the denominator. All right, so that should be an 8x, excuse me, copy error. All right, and then 15. And so if we take a look, the degree of the denominator and the degree of the numerator are both 2. Okay, just like we had in the previous video. So degree, both 2. And so what we do is we take the coefficient of the leading coefficient of the numerator and the leading coefficient of the denominator. And so that would be y equals -2 over 1, or y equals -2 would be our horizontal asymptote. Now, just like before, what I'm going to do is I'm going to find the holes first. Okay. To find the holes, what we need to do is we need to factor both the numerator and the denominator completely. All right. Now, what I'm going to do is I'm going to factor out a -2 from here. Okay, so if I factor out a -2, what that's going to do is it's going to flip the signs around. Okay, so we could either write this as -9 plus x squared, or what I'm going to do is just flip those around and write it as x squared minus 9. Right? So that's going to be x squared minus 9. Right? And then in the denominator, we already factored that, remember? And that's one of the benefits of finding the domain, is that we already have the factored form generally. Now, in the numerator, notice that what we can do is we can factor the difference of squares. All right, so remember x squared plus 9, we can factor as x plus 3, x minus 3, and then x plus 3, x plus 5. Now, I want you to notice that there is a common factor of x plus 5, or x plus 3, excuse me, that exists between the numerator and the denominator. So that means that there is a hole in the function. Okay, so what that means is that there's a hole when x plus 3 is equal to 0, or when x is equal to -3. Okay, so that's where there's a hole is, right? Or where a hole is for this, right? However, to find the y coordinate, what we have to do is we have to substitute this when we cancel this out. So we're going to cancel these. And to find the y coordinate, what we're going to do is we're going to substitute the -3 back in. Okay, so when x equals -3, then we get -2 times -3 minus 3 divided by -3 plus 5. Okay, and so the numerator is just going to turn into -2 times -6, or that's going to be -12, or +12, excuse me. And the denominator is going to be 2, so 6 is going to be the y coordinate. So what that means is that there is a hole at the point -3, 6. Okay, and we'll see that a little bit later when we graph. The final thing we do is we find the vertical asymptotes. And that's what, when we do that, what we're going to do is we're going to take this simplified expression, okay, and we're going to set the denominator equal to 0. Okay, so that's actually really easy. So to do that, that's going to be negative 2x minus 3 divided by x plus 5. The vertical asymptotes are going to occur when x plus 5 is equal to 0, or at the vertical asymptote is x equals negative 5. Right? Now, let's go through and make sure all this makes sense. Right? So I'm going to go ahead and graph this. And our original function, a bit of a pain, but that's okay. So it was 18 minus 2x squared, and then we had x squared plus 8x plus 15. Oh. All right. So, and let me get rid of these lines because we don't need those anymore. They were from a previous problem. All right. So remember, one asymptote we had was y equals negative 2. All right. And again, just going back here, so y equals negative 2. And then we also had, I'm going to plot this point, negative 3, 6, and then we also had x equals negative 5. All right, so we can clearly see that both of those make sense here. Okay, so it's following this asymptote. If I zoom out, we can see it's even more prevalent. All right, and then finally we had the point negative 3, comma 6. Right, and so we see it right here. Now that's a hole. All right, so that point on the graph does not exist. Now if I get rid of that hole, all right, notice that we can't really see anything. Okay, but if I go through and try to see what Desmos says about that point, so be really careful. Notice right here it says negative 3, comma undefined. So there actually is a hole there, okay? And Desmos is smart enough to find it, okay? We could just plot it on the graph and we can see it that there is a hole there. Okay, so that's pretty cool that we can identify these just by looking at the various components of the function. Now let's take a look at one last example. And this one's a little bit easier than the previous. So we have x cubed over x squared minus x, right? And again, we look for the domain first. Okay, so we set x squared minus x equal to 0, or not equal 0, excuse me. And so we're going to factor in x. And so one factor is when x cannot be 0, and the other one is going to be 1. Okay, and that's just because x minus 1 cannot be equal to 0. So that means x cannot be equal to 1. All right, so our domain is going to be x is an element of negative infinity up to 0, union 0 to 1, union 1 to infinity. All right, so there's our domain. The next thing we're going to do is find the horizontal asymptotes. And that's where we take a look at the degree of the numerator and the degree of the denominator. Now, we take a look at this, and it has a degree of 3. And then we take a look at the denominator, and it has a degree of 2. So we have that the degree of the numerator is greater than the degree of the denominator. And so if that's the case, let's go all the way back up and remember that if the degree of the numerator is greater than the degree of the denominator, there are no horizontal asymptotes. So the three examples we've looked at so far, they've all had horizontal asymptotes. This one doesn't. Okay, so we would just say that there are no horizontal asymptotes. All right, so next thing we're going to do is we're going to find the holes. Okay, and remember, I said that holes was part 4. So remember, we have x cubed over x squared minus x, and we would factor both the numerator and the denominator. Okay, so we factor out an x, right? And I want you to notice that there is a common factor of x that exists between these. Okay, because remember, we could write x cubed as x times x squared. Okay, so if we really wanted to factor x cubed, it's not completely prime, okay, but we can factor it like that. And just like before, what we can see is that right here there's a common factor, okay? So that means that there's a hole at x equals 0. So remember, all we do is we just set one of those factors equal to 0, okay? Now, to find the y coordinate, in this case, it's actually really easy. All we're going to do is we're just going to cancel these out. and we're just going to substitute 0 back into the simplified version, okay? So when x equals 0, that means we get 0 squared over 0 minus 1, which is 0 over negative 1, which is 0, okay? So that means that there should be a hole at the origin, okay, at the point 0, 0. So hopefully that makes sense and that's not too difficult. Okay, pretty easy, I think, when we go through and we just factor and simplify. And then the last thing we do to find the vertical asymptotes, it's easy. At this point, we just take the simplified version of the function. So we just take x squared, x minus 1, and we set the denominator equal to 0. All right, and so that means that there is a vertical asymptote at x equals 1. Right? And so finally, what we're going to do is let's just check all this. Okay, so no horizontal asymptote, hole at 0, 0, asymptote at x equals 1. All right, and obviously the domain will be taken care of by everything else. Okay, so we have x cubed over x squared minus x. And the only asymptote that we have is x equal 1. So remember, there's no vertical asymptote. So we would have x equals 1. Okay, that's certainly an asymptote here, right? And then remember we had the point 0, 0. Okay. Oh, sorry, this should be x squared minus x. Excuse me, that's a typo. Okay. Um, and then let me get rid of this point because we don't need that point anymore. So remember we had the point 0, 0, and it said it was going to be a hole there. I don't know if I can zoom in particularly on that. Let me zoom in just a little bit more. All right, and then right there it says 0, comma undefined. And if I move my mouse just slightly, we can see the hole. Okay, so there, no hole, and then there, hole. Okay, so I would just plot the point 0, comma 0. Okay, and that's where the hole might be. Okay, this graph actually exhibits something called a slant asymptote. Okay, and so if I was to find the equation of the slant asymptote, there would be an equation that just kind of goes this way. Okay, in this course, we're not going to take a look at slant asymptotes, but basically it's going to be this diagonal line to where the function becomes asymptotic. Okay, but again, we're not going to look at those in this course. Okay, so those are various asymptotes for the functions. Okay, and also the holes. Now that leads us up to the point where we can take all this information and similar to what we did with polynomial functions to sketch a rough graph, what we're going to be able to do is we're going to be able to use a systematic process to be able to sketch a rough graph of these sorts of rational functions. And we'll do that in the next few videos.